Welcome to Brain Vision.
Once again, welcome to a new problem. We are going to be dealing with a spring. We're going to be dealing with a spring this time. So we have a spring that's not stretched yet. So we're going to call the initial position x naught equals to 0. And then the other things that show up in the spring, that's the force of the spring. We also talk about the spring constant. The other thing that stands out is the fact that there's going to be a 12 joules of energy being put into the spring to stretch it a distance of uh, 3 centimeters. So x1, the next distance will be 3 centimeters. You change that to meters, so multiply that by 1 meter over 100 unit conversions. And so this becomes 0.03 meters. That's how much you stretch the spring. It's going to stretch that way in the positive right direction. So this side is positive and this side is negative. That's going to affect the outcome of the problem. The energy required, if we use the work energy theorem, is the initial position of the spring, the final position of the spring, 1/2 kx1 squared minus 1/2 kx naught squared. Remember this formula right here. This is the energy in a spring. So this is the energy in a spring. If you can recall from previous problems, we also had kinetic energy, different formulas, but this one is a little bit different. It's 1/2 kx squared. For kinetic energy, it was 1/2 mv squared. The other thing you're dealing with is the forces involved in stretching the spring. So a typical spring force is kx, but we contextualize it to this problem. So we're going to have k, the final position minus the initial position, which is 0. So those are the parameters we're dealing with. Those are the variables we're dealing with. Part A of the problem, we're going to use the energy equation. And it's saying we want to find the spring constant K. That's our goal. So if the work done in stretching the spring is 1/2 kx1 squared minus 1/2 kx naught squared, this part is going to be 0 because sorry, not the final position, but the initial position is 0. Okay, so this initial position right here is 0. That's going to make the whole energy at the beginning 0. The energy used to stretch the spring is 12 joules. And so we want to solve for K. It's always a good habit to use the variables and plug in at the end. So Ws, which is the energy in the spring, equals to 1/2 kx1 squared. Divide both sides by 1/2 x1 squared. 1/2 x1 squared. Remember, this 1/2, when it comes up, it becomes 2. So K has to be 2Ws over x1 squared. And then we plug in the numbers 12 joules all over 0.03 squared. And that's going to give us the spring constant K being equivalent to 2.67 times 10 to the 4 Newton meter. That's the spring constant. In the second part of the problem, we want to find out the force involved in stretching the spring a distance of 3 meters to the right. So remember, it's kx1 minus x0. And so K happens to be 2.67 times 10 to the 4 Newton meters. x1 is 0.03 meters. Remember, x0 is 0, so we can ignore that. You plug in those numbers and get 801 newtons. The final part of the problem in part C, the opposite happens. So the opposite happens where we have the spring, and I'm going to do that in the next page. We have the spring right here. The initial position, x0 equals to 0, or you can call it 0 meters. But this time the spring is being compressed, so it's moving in the negative direction. And it's compressed a distance of 4 centimeters. Change that to meters, so conversion units, x1 becomes 4 centimeters. It's moving in the opposite direction, so we put a negative, so you get negative 0.04. That's the displacement on the spring moving towards the left. And that's the number we're going to use. Using the work energy theorem for the spring, we have 1/2 k x1 squared minus 1/2 k x0 squared. This is going to be 0 because x0, as you can recall, is 0 meters. And so our W, the energy in the spring, becomes 1/2 k. Doesn't change for the spring because it's based on the material. 2.67 times 10 to the 4 Newton meters times negative 0.04 meters squared. Remember, we don't have to put this part of the problem. That's the initial energy in the spring, which happens to be 0 because the spring hasn't been compressed. You plug in those numbers, you get 21.4 joules. So remember, that's what you get in terms of energy. In terms of forces in the spring, you still use the force formula for stretching the spring. So we want to find out what's the force in compressing the string, not stretching. This is in the opposite direction. So x1 minus x0. Remember, x0 is 0. So we plug in the numbers. 2.67 times 10 to the 4 Newton meters times x1, which happens to be negative 0.04 meters. And that gives us a final answer of negative 1070 newtons. Negative 1070 newtons. Remember, it's negative because we're moving in the left direction. So the left is negative and the right is positive. I hope you enjoyed this problem. Feel free to send any questions my way, or if you have any comments. And this is just a different way of studying energy when it comes to springs. Thank you very much and have a wonderful day.